Just fold my screen. Okay, so let's get started. Okay, let me just try. So this is the first time we are doing this. It's getting a bit confusing, but we will do our best as much as you can. Hopefully nothing breaks. Okay, ouch, my finger. Okay, so here we are. Oops. Okay, so we're actually on tutorial 3. So we are looking at probabilities now. Now, first and foremost, what is probability? Okay, can everybody hear me, right? If you can hear, just raise up your hands. Otherwise, I do not know. I can say something. Okay, good. Alex, you can hear, means the rest can hear already. What does probability means? Can somebody want to say something? What is probability?
The chance of something happening.
Okay, basically, when you answer anything, tell me who you are, because I definitely cannot hear you.
Oh, okay. Sorry.
Chance of something. Okay, the something can be an event or even events happening. Correct. Okay. So that is essentially probability. Now, is probability bound by a certain value? It means, is there a upper boundary and lower boundary for probability? Let's say probability, is there a upper and lower boundary?
Yes.
Yes. Okay. So what is the boundary?
0 and 1.
0 and 1. Okay. Now, when you have 0, it means that the event.
Which I think is it the wrong side?
Yeah, correct. It's the wrong side. So this is 0. This is oops. That's the wrong thing. 0. This is 1. Okay. So anyway, erase. Oh, okay, 1. Okay. So here, 0 means that it is a impossible event. Okay. No chance of it happening. 1 means that it will certainly happen. All right. So that is the basis of probability in itself. Now, when we talk about probability, we also say that, for example, what is the probability of event A plus the probability of event A not happening? For example, what is the probability that it will rain and the probability that it will not rain? What will be this?
1.
1, okay? So you can sum up the probabilities in that sense. Okay, probability that it rain and probability that it will not rain. Okay. So that is actually very important. Now, how do you actually describe a probability in numerical terms? If you have to have a ratio, what is a ratio? For example, how do I know that the probability that it will rain in Singapore is, let's say, 20%? How do I get something like that?
P rain over P rain plus P not rain.
Okay. So basically, you are saying that it is the number of days or number of events versus number of the total. Okay, so in this case, you're right. It's actually the probability of rain, the number of days that it rain, versus the total number of days. Okay, so these are very important concepts. Okay. Now, then we will go through the next one. Let me save this. Get the hell out of here. Save it. Yes. Okay. New one. But not new one. Okay. So let's say, for example, I say that in Singapore, the probability that it rains is, let's say, 20% of the time. Okay, and Singapore, our daylight is actually quite constant, so the probability of day is 50%. Okay, so if I want to ask you what is the probability that it rain during the daytime, how will you calculate that? Anyone? Let's see, Clara.
P rain then times P day.
Correct. P rain times P day. Okay. So in this case, you are talking about a Venn diagram, rain and day. You are looking at the intersection. So in this case, is 0.2 times 0.5 gives you 0.1. Okay. When the probability, when you multiply, if there is no intersection, okay, if no intersection, then that is what we call as a mutually exclusive event. Okay, so this is actually quite important. So probability you can multiply, you can add together. All right. Now, so let us do a very simple question first. Let's say that you're playing dice. Okay, and you have two dice. Two dice. Okay. What is the probability of getting a 8? How many ways you can throw two dice to get 8?
3, no.
Say 3, 6.
Huh? 3 what?
6.
Can you, if one dice is already a 1, can you ever get 8?
Cannot.
Not right,
6,
because there's no 7. Okay, so you have 2, 6. What's the next one? 3, 5. 4, 4. Then the opposite way is 5, 3, 6, 2. So there are out of 36 outcomes. So in this case, it will be 5 outcomes out of 36 outcomes, which is around 17% or so. Yeah, I just basically calculate off my head around 17%. Okay, so you are able to know this context pretty well. So this is actually quite important. But there's actually one more component that I want to cover, is this thing called area under the curve. Okay. Because what happened is, if you look at what a 17% means, is you're taking 5 possible chances out of 36 possible chances. Okay, which means that we can calculate what is area under a curve and make it into a probability. Okay, so let me just save it up. Save. So let's play a dice game first. Okay, so we have 2 dice. Okay, now what is the smallest number that you can get from 2 dice?
2.
2, right? So to get 2, what is the outcome? What is the number that you need to get?
1, 1.
Okay, so 1, 1. That's only one. Okay, so to get 3 dice, 3. What do you need to have? What is that? What the dice show?
1, 2,
1,
2.
2 or 2, 1.
Yeah, 1, 2, or in this case 2, 1. Okay, how about 4? Somebody else? Let's say Dexter.
1, 3.
Okay, 1, 3. Any more? 2, 2. Any more?
3, 1.
Yeah, 3, 1. Correct. Okay. 5. Maybe let's have, I can't even see your name here. Alex?
So got one more 3, 2, right?
3, 2. 3, 2, 3 and 2 is 5 already.
Yeah, there's 2. Oh, sorry, forget.
So, okay. So for how to get 5 outcomes? What are the ways of getting a 5?
4, 1.
Okay, no, let's start with 1 first. So 1, 4, then what are the options?
2, 3.
2, 3. Any more?
3, 2.
3, 2, correct. And 4, 1 here.
Yeah.
Okay. To get 6, somebody else? Just any random, any person that you want to say?
1, 5.
1, 5. Okay. Any
4.
more?
2,
2,
4.
4.
3.
3, 3. Any more?
4, 2.
4, 2.
And 5, 1.
Correct. 5, 1. Okay. 7. Somebody? Daniel?
Oh, I just
Okay. Okay, then Daniela?
6, 1.
Let's start with 1, 6 first lah.
Okay, 1, 6.
Okay.
2, 5.
2, 5.
4, 3.
4, 3. 3, 4. 4, 3.
Yeah, sorry.
Okay. Then
5, 2. Is it?
4, 3. Then 5, 2.
Oh, yeah. Okay.
Otherwise, you get confused. Then after that will be 1, 6.
6, 1.
Yeah, 6, 1. 6, 1. Okay. Let me just take this small eraser, stroke erase. Can I do a stroke erase? Yeah. Okay. Okay, 6, 1. Okay. How about 8? Somebody else? Anyone? Sherwin, for example? Is it Sherwin?
1726.
How to have 1, 7? How to have 1, 7?
Sorry.
Yeah.
4, 4.
No. The smallest one? Yeah,
2,
4, 4.
2, 6.
No, not below that. So you have 2, 6. Yeah, 2, 6. Okay. Then after that?
3, 5, 4, 4.
3, 5. Correct. 4, 4. Any more?
5, 3.
5, 3. And
6, 2.
6, 2. Okay. 9. Okay, next. Tong Tai?
Hello.
Yes.
3, 6.
3, 6. Correct. Next one.
5.
What?
4, 5, 4, 5.
4, 5.
5, 4.
5, 4.
6, 3.
6, 3. Okay. 10. Okay, anyone, just, okay. Because I can't see your name here. I could try to remember your name. Darren?
Yeah.
Yeah, so 10. How do you get a 10?
4, 6.
4, 6. Any more?
5, 5.
5, 5.
6, 4.
6, 4, correct. Okay, 11. 11. Who is okay. You know, on my tablet I can't see your name fully, so must well you just tell me somebody. Clara already answered. Okay. Hannah? Is Hannah around?
Hi.
Hi, 11.
5, 6.
5, 6, and?
And 6, 5.
6, 5, correct. So 12, there's only one, 6, 6. Okay. So this is a probability by itself. And if you remember from your secondary school, you actually can draw a frequency polygon. Okay. Now this frequency polygon covers all the thing, which means that the area underneath it, the area underneath the curve, the frequency polygon, equates to 100%. Right? Now, if you have that, when you say that the probability of getting a 12, okay, you are taking this portion 1 out of all the likelihood, which is 36. Make sense? If we draw an axis here, this will be your frequency, which means that, let's say if I can get an equation for my red line, my frequency polygon, okay, the equation here will be frequency equals to a function. Okay, the x is the number. Now, mathematically, for those who have done A maths before, how do you find the area under the curve from the line itself? Anyone?
The line straight.
No. Let's say if I give you the equation of a line, how do you find area under a curve mathematically?
Integration.
Correct. So in order to find area under a curve, which is area, the area under your frequency polygon is actually equals to the probability, which is you can do integration of the line itself. So this is a very important concept, and that's all you need to know about integration. I'm not asking you how to calculate the integral and so on. Okay, this is actually not part of the syllabus for chapter 3, but it's an important concept for you to know for subsequent lectures. Okay, when you talk about tests and so on. Okay, any problem with this idea? Any problem with this idea so far? Yes, no? Okay. So if not, we will go to this thing known as your conditional probability. Now, conditional probability, when do you use it for? When do you use conditional probability? Anyone? Anyone want to say something?
What you mean when you use
When?
it?
Yeah, when do you use it?
When something given something.
Yes, correct. So you want to find the probability of an event given that another event happened. Okay. So that's how you use conditional probability. So let's look at an example. Okay. So let's say we have the probability that it will rain in Singapore is again 20%. Okay. And let's say I tell you that John takes cab when rain. So John takes cab when rain, he will take cab about 70% of the time when it rains. But John also take cabs when it doesn't rain, but at lesser chances. Without rain, maybe he take cab only 20% of the chance. So what I want to find out is, what is the probability? Let's say, for example, now, okay, let's say today, you say you know that it is raining. Okay. So what is the probability that John is taking a cab to school, given that he has not come in yet? So in order to do such question, you have to start to draw the tree diagram. So the tree diagram, you draw it out. You have rain versus no rain. So the probability that it rains is 20%. probability that it doesn't rain is what?
80%.
80%. Okay. So rain itself, you have the probability of taking a cap and the probability of no cap. Okay. No rain, same thing. But the probability of rain when taking a cap is already given here, is 70%. So the next one is 30%. These two have to add up to 100%. So if no rain, also possibility of taking a cap and the probability of not getting a no cap. No rain and taking a cap is 20%, given here. No cap is 80%. So in this question itself, what is the probability that John is taking a cap when it is already raining? So you're looking at probability of cap when it is already raining. So the equation here is the numerator is probability of cap and rain. Divide by the probability of rain. So in this case, the probability of cap and rain is 0.2 times 0.7. Okay, it's actually this. Okay, 0.2 times 0.7. Now divide by the probability of raining, which is 0.2. So in this case, the probability of John taking a cap when it's rain is 0.7. Just divide. So far, any problem? Any problem so far? Okay, assuming there's no problem, let's look at the next question. What happens, let's say, if we reverse the question? Let's say now you are in a lecture theater and John comes in, says his cab fare is expensive. Basically, he's taking a cab already. So now, what is the probability that it is raining? Because in a lecture theater, you can't see it outside. So what you need to do is a reverse. Probability of raining when John is taking a cab to school. Okay, the equation will be the probability of taking a cab when rain divided by the probability of taking a cab. Okay, so this is a bit more complicated. What you have will be here. Let me find another space, right? Okay. Okay. Let me just erase this. And I kind of just write at the bottom. Okay. So probability of taking a cab when rain is still the same. Cab and rain, 0.2 times 0.7. So it is actually this part. The denominator is cab, but there's actually two cab. This is a cab, this is a cab. So you have to divide by, divide by both. You have 0.2 times 0.7, which is given by the blue track. And you have to add to this part. Okay. I need to use a different color now, otherwise you can't see. 0.8 times 0.2. Okay. So can somebody help me calculate? What is the answer? Take out a calculator, help me calculate the answer. Sabrina, any answer? Or Noel?
Do you want like decimal places or the fraction?
Decimal places, please. Always give in decimal places. Don't give me fraction during exam or test.
Okay. 0.467.
467, correct. Okay. So now you actually see something quite important here, which I'll mark it in red again. It means that the probability of event A given event B has happened is not equals to the probability of event B given that event A has happened. So this is a very important concept. Okay? These two probabilities are different. Cap when it's raining or raining when it's cap. Okay, these two probabilities are very, very different. Make sense? Okay. No, then assume that you understood. Okay. So the next one that we have, let me see, about this, actually save this screen properly. Okay, good. Save it properly already. Okay. So the next thing we want to talk about is your contingency table. So when you have your contingency table, what is the rule? Which one is the outcome in columns or outcome in rows?
On top one.
Huh? Outcome in
On top one.
Means, yeah, outcome will be in rows. Okay, the exposure in your outcome in columns, exposure in rows. Okay. Okay, so what we usually have is something that looks like this. You have the outcome, positive outcome, negative outcome, positive exposure, negative exposure. Okay. And by convention, we say that this is A, B, C, and D. We calculate the 4 numbers. All right. But what we actually can do before we calculate these 4 numbers is something else. We can calculate what is the probability of a positive outcome. So if we calculate a probability of positive outcome, it means that this is A divided by A plus B. This is C divided by C plus D. Okay. In other words, the probability of having a positive outcome is also known as the risk. From then on, relative risk is the ratio of a positive outcome given the exposure against the positive outcome without the exposure. Okay, and this gives you the equation that you are familiar with, which is A divided by A plus B and C divided by C plus D. Oops, happened. Stroke eraser, small eraser. Okay, so far any problem? All right. Now, out of A, B, C, D, which one do you think is a bigger number? Which one do you think is usually the largest number? A, B, C, D. Which one do you think is the largest number most of the time?
E.
Yeah, okay. So D is usually the largest number. Okay. And by extension, we say that B plus D is almost always much larger than A plus C because we usually have no outcome rather than have outcome. Okay. And because of that, we also can say that A is almost always going to be much smaller than B. Okay. And C is almost always going to be much smaller than D. Because of this, okay, we can approximate A and B to be 0, okay, in the denominator. Not the numerator, only the denominator. And what this happens is, if you put it back into the equation for a relative risk, we have A divided by A, which is 0, plus B. C in the numerator, in the denominator is 0 plus D. This gives us back to A divided by B, C divided by D, which is then what we call as the odds ratio. Okay, that's how the two things come about. Okay, all right. So that's essentially contingency table. Nothing very sophisticated about it. Stupid laptop.
Sure.
What?
Wait, you say, can you go back to the, you look at the A over A plus B, C over C, over C plus D, that one, right? You say A and B to be 0, we approximate that it's 0 in denominator.
Yeah.
Then why the C is involved?
No. A and B. Oh no, it's A and C, not A and C. A and C, not A and B. This A and C.
Okay.
Okay, small. Okay, stupid. Okay. Yeah, A and C. Okay. So yes, let me just save this again. Hello, do you want to save or not? Okay, this is killing me. Let me try again. Hey. All right, so with that, we can go on to your tutorial question. And tutorial question, let us start with question number 2.
Wait, teacher.
What?
Why odds ratio can odds ratio can be used for like everything when they assume the thing is 0, then sometimes the case is not 0.
Yes, so it's approximation. It's not an exact way of calculating. It's just an approximation. That's the main thing.
But let's say it's like, cause maybe you talk about, maybe the unit express, right, is like 1 to 100 U.
Yep.
But maybe U is like 1000 so like the thing you're assuming is 0, right? It's actually like 1000, and isn't that like a lot?
No. So it's because, okay, let's see. Now I have to go back here. Now it's because that you assume. Okay, let me just get back, which I can't get back. Let me just turn my laptop again. And one day I'm going to break my laptop by doing this. Okay, let's see. And where do I have? Okay, yes. Okay, this. Okay. No, because this is a picture already, I can only do this. Okay, because what happened is most of the time, your B, these two numbers are actually much larger because usually we have no disease rather than have disease. So it's almost never that your A is the same magnitude as your B. A is usually very small, B is usually very large.
I know it's usually small, but let's say for example, the disease suddenly very widespread, then how? Then
Okay,
suddenly
then you cannot use it. You cannot assume this to be zero already.
Then you must go with relative risk.
All right.
Oh, okay.
And now what do I have to do here? Okay. All right.
Wait, Dr. Ling.
What?
Wait, I have a question. So, because you said that, right? Am I right to say that if the relative risk is lesser than 1, then the relative risk should be bigger than odds ratio, then vice versa, which is when RR is bigger.
Okay. Yeah. Okay, so you just make me remember a point which I haven't touched about it yet. And let me go back. And what am I supposed to do here? Hello, you can see my head? Yeah, you can see my head. Okay, so it means that, okay, when relative risk is approximately 1, okay, what does it really mean here? What does it infer?
No relation.
It's actually not more than no relation. It means that the presence of exposure. Okay, let me hit this color. Just it means that the presence of exposure does not increase the outcome. Okay. In other words, in biological terms, it could be the situation whereby the presence of exposure could be smoking does not increase the outcome, can be obesity. Okay. But remember that your contingency table is a binary option. That means you have to quantify what is smoking. Is it heavy smoking, light smoking, casual smoking? How many cigarettes a day? What is obesity? Is BMI above 30? That is obesity, or BMI above 28? You consider that as obesity. So it does make a big difference. Okay. On the other hand, if the relative risk is more than 1, it means that the exposure increases the probability of outcome as compared to no exposure. Okay. If the relative risk is less than 1, means that the exposure decreases the probability of outcome as compared to no exposure. Okay. So in less than 1, it could be a situation whereby exercise 3 times a week. Okay, this is your exposure. This is your exposure. Okay. Reduces cholesterol. Okay, so this is, oops, maybe different color. This is the outcome. Okay. As compared to no exercise. Okay, so this is how you interpret relative risk and odds ratio. It increases or decreases the risk. Okay, of course, there's actually another way is to calculate what is the increase and is it significantly increased, but we'll come to that pretty much later. We'll not bother about it first. Okay, so let me save this. Okay. Okay. Now with that we can do our tutorial questions. So our tutorial question, let's start with question number 2. Okay. Question number
skip 1.
1 is always a big problem, so we always skip 1 first. Now, as you realize that question number 1, right, the true false question, it is testing a lot on your English rather than, yeah, it's very language based. So we skip 1 first. Okay. Now, question number 2, we look at, let's say, the probability of having a disease in the population. The probability of the disease in the population is, let's say, 20%. Okay. Now, if the person, anyone with the disease and tested positive is 90%, 0.9. Okay. Which means that a person can have the disease and it is tested negative. Okay, this is 1%. Okay. But you also can have a person without the disease and is still positive. Okay, that itself is given by a question 0.05. Probability of no disease and negative is then 0.95. Okay. So let's draw our tree before we do anything. The question is to ask, what is the probability of having the disease when the test is positive, when a positive test. Okay.
So can I use the percentage instead when I do the tree diagram?
You can. Just make sure that you put everything correctly.
Okay.
Yeah. Okay. So remember, our probability must be 100%. So when you use percentage, make sure when you convert into calculator, you divide by 100. Don't mess it up. Okay. So we have disease and no disease. Okay, so this is D plus, this is D minus. Okay. So the probability of having disease in the population is 20%. No disease is actually 80% then. Okay. Test positive, test negative. So a person have a disease and the test is positive is also given in the here as 0.9. So this is 0.1. Okay. If a person doesn't have a disease and is tested positive, is 0.05. Here is 0.95. Okay. So the numbers come from here. You have this comes from here. Okay. And this is from here. This is here. This is here. Okay. And finally, you have this, which comes here. Right? So what does it mean? Okay. If a person has the disease and is tested positive, this is what we call as, is again upside out of syllabus, this is the true positive result. If a person has the disease and the test come out to be negative, this is called a false negative result. But a person is healthy, doesn't have disease, and the test come out positive. This is called a false positive. Okay, and if the person doesn't have the disease and comes out negative, this is called the true negative. Okay, so these are some of the terms that you can use. Then let's calculate here. So what is the probability of disease when the test is positive? You have the probability of disease and test positive. Divide by test positive. Okay, so let's look at this. Disease and test positive, there's only one track that you can use, which is here. This is a disease and positive. Okay, which is 0.2 times 0.9. Okay, now, but there are two positive. Okay, this is also a positive result, this is also a positive result. So you have 0.2 times 0.9 first, plus, this is the same here, plus you have the second track, which is this. Okay. This is 0.8 times 0.05. So if you calculate everything right, what will be your answer? Anyone? Yola, what's your answer? If you haven't calculated, then they got to calculate. Hello, anybody still there?
Yes.
Okay. Answer?
I got wrong lah.
You got wrong ah. Okay. So anyway, what?
I thought it's contingency table, bro.
No. This is nothing to do with contingency table yet. You can use contingency table, also the same thing. Okay. So the answer here is 0.82, which means that the probability of having the disease when the test is positive is 82%. Okay. Just like what you did in primary school, make sure you write the statement, okay? The conclusion statement. Now, does it appear strange to you that you have a very reliable test, 0.9%? But when the person is tested positive, he is only on 82% of having the disease. It's actually lesser than 0.9. Does it appear strange to you?
Wait, can you repeat what you said?
Okay. You see, although the probability of the test being the test able to pick up the disease is actually 90%. This one, probability of disease and test is 90%. Okay, but when the person is tested positive, but he's only 82% chance of really being infected. 82% is lesser than 90%. Is that strange to you?
No leh.
No, okay. Now the reason is because of the false positive. We can actually skew this number to be even greater. And let's just work a different number. Okay. We work this and let's see what we can get. I am going to hit this computer. Okay. Did I get the right thing? Did I save this thing already? Okay, good. Okay. So let us just do one more type of similar question and say that the probability of a disease in the population is maybe 0.005%. So low probability. Actually, 0.005 is actually not low probability. Okay. Or let's make it even more realistic. Let's say a probability that we know of HIV infection in the population is 0.001%. Okay, so it's about 1 in 1,000, even less than that. But the test, okay, if a person is infected and so the let me see. Okay. So the test being positive when the person is actually HIV positive is actually a very high chance, maybe 0.995. So the test is actually pretty good at picking it up. But because it's so good at picking it up, it is also possible that the test is positive when the person is actually HIV negative. You may have 1% chance. Okay, so in another words, what I'm saying is this is the false positive rate. Okay, this is the true positive. Okay. So then my question becomes, what is the probability of the person being HIV positive given that the test is positive? Okay, so let us draw the table, draw the diagram again. Okay. Now we have positive. Here we have 0.001, which means that this is 0.999. Okay. However, test positive, test negative. If a person have HIV and is tested positive, it is 99.5% chance. So means that 5% chance he is negative. Okay. However, if a person is HIV negative, you still have 1% chance of being positive here, but 99% chance of being negative. So then let us work out this problem here. Okay. Probability of HIV positive and the test is positive. Okay. Versus that the test is positive. Okay. So HIV positive and test is positive is very simple. This track. Correct. So we take this. 0.001 times 0.995. Okay. Denominator is also 0.001 times 0.995 because it's the same track. Okay, but we have the second set of people, which is here. This is also tested positive. Okay. Okay. So this is 0.999 times 0.001 at 0.01. Okay, so can somebody take a calculator and help me calculate what is the probability now? Anyone, quickly?
100.1.
Where got 100.1? How to be 100.1?
Oh no, I type the calculator like that.
Calculate again. How do you 100.1? Make sure you put your brackets properly.
Never mind, 0.09.
0.09. Yeah, 0.09. Correct. So which means that, in fact, this is quite a realistic case. Okay. So this is roughly the proportion of your ELISA test. Okay. That means when a person is tested positive on, let's say, your HIV ELISA test, there is really only 9% chance that the person is really infected with HIV. Okay. So what I'm trying to point out to you is look at this number versus this number. People think that when you test the first time HIV, first time on your ELISA test or your screening test, you are almost certainly to be HIV positive. Actually, it's not. Most of the time, you are false positive. That's why after the ELISA, you have to go through the second test, which is your Western blot test. Okay, and yet there are people who try to kill themselves at this point. They get very, yeah, correct. You have only 9% chance there. Even the test is very well. Okay, the real number is 0.05, which means that you are only 1 in 20 chance that you are still positive. However, for HIV, the last time I calculate was 20 years ago. If your Western blot and ELISA tests are both positive, okay, the chance of being, the chance of actually that you are a false positive, right? That means you are really negative is only 1 in 2 million. Okay, so that's not very good. Okay, but this is the case.
Oh wait, sorry, can I confirm? You wrote there's only a 9% chance that the person is infected with HIV.
Yes, when the first test is positive in this case. But of course, that you have to look at the actual test numbers because these are made so-called numbers that is more or less in my head. The numbers now may change.
But then the chance like damn low, yeah, what the hell? Then the test like not accurate ones, yeah.
That's why you always have to go for the second test. It's very important. Similarly, now your bio students, your especially your mother will be going through their annual mammogram now or biannual mammogram. So mammogram is a screening test. Okay, you could appear your mammogram to ask you to go for a second test, and most parents, most mothers will be worried that you have breast cancer now. Most of the time, you are quite fine. Just calm them down and go for a second test first. Don't panic. That's what I'm trying to say. Understand or not?
Yes.
Okay, good. Okay.
But then you negative for the first test, then how will you go for the second test?
If you negative for first test, then you're quite fine already. You're negative for first test, you're quite fine. Okay, because why? If you are, okay, so the question is, if you are negative for the first test, okay, that means you fall into this category here. So you can calculate what is the probability that you are really negative when the test is negative. Okay, the chances is actually very high because it's the reverse. Okay, in this case, you'll be taking 0.999 times 0.999 over 0.999, which is this track, times 0.999 plus, of course, you have this opposite one, 0.001 times 0.005, which is still nearly 100%. Who is the one that asked me just now?
Oh, Alexander, yeah, okay, cool.
Correct. Okay. So usually the first test is to capture all the people that needs to go for the second test. If the first test is negative, you are almost certainly to be okay. If the first test is positive, then yeah, a little bit of concern, go for the more precise test. That's what I'm trying to say. Anyway, since Alex, you are the one calculating, can you actually calculate this number?
Yeah, I'm typing now.
Yeah, so what's the answer? Okay, so it's 0. Yeah, anyway, I draw one more 9 already.
It's 1.00.
Yeah, correct. It is almost 100%. That's what I'm trying to say. You know what I'm trying to say? Yeah?
Yep, got it.
Okay, so please don't since you're here, if test negative, okay, so let me just box this up. If negative for first test, almost certain that you are fine.
Sure.
What?
Then you cannot just straight away go Western block, man.
Western blot is expensive.
Oh, okay.
Okay, and Western blot, you need to go to the lab to do Western blot. But you ELISA test, all this, you can do a dipstick test. These days, you can do HIV test by using your saliva.
So cheap lah.
Cheap and fast lah.
But way too lah.
It is accurate as a screening for you to go for second one. So it's accurate to differentiate whether should you be going for the second test or should you absolutely fine already.
Teacher, what does that say? If negative for first test, almost certain that you are what?
You are fine. Okay, you are fine. You're okay.
Okay.
Okay. Yeah.
But teacher, you say like it's almost 100%, right? So like it's not 100%.
Okay, so what happened is that's why if you're worried, then go for another test. Then every year you just do a test.
I need to check every year one.
Actually, you're supposed to check every 6 months if you're sexually active. Okay, whatever. That is not my concern. Okay, now. Where am I already? Question 2. Okay, I'm down. Okay, so question 3 works out to be the same way. Question 3 is the one that the probability of a rare disease is 1%, right? Is that, am I getting the correct question?
Yeah.
Okay, so if you get it correctly, question 3, your answer is actually 50%, 0.5. Okay. All right. Question 4 is what? What is your question 4? Is the one talking about the penformin or the cake one? Some human respond.
Cake.
Cake. Okay, question 4. Let's do it. Question 4, cake. Okay. All right. Now this is a little bit sad problem, but the relative risk, what do you get? Okay, Dexter, what's the relative risk? Dexter.
Hello?
Yeah, what's the relative risk for question 4?
1.4.
1.4?
Wait. Oh wait, that one I haven't do. I'm sorry.
Okay, so who have done question 4? Question 4. Yeah, question 4.
For the answer online, 6.13.
Yes, 6.13. The answer is right there already. Okay. So Yeah.
Oh wait, I thought question 4 was you have to look at the proportion of patients.
Yeah, so we're talking about portion now. So the portion, the fraction of 54 over 79 is actually 54 over 79 is basically those who are ill and attended the wedding. Okay, which means that the best answer using the blanks, right, is this is the overall attack rate among persons who attended the wedding. Okay, so the fraction 50 over 54. 50 over 54 is basically those ill and ate the cake. Okay, those ill and ate the cake. So in this case, it is the best answer is the proportion of patients who ate wedding cake, because there are also some that are sick without eating the wedding cake. Fraction 50 over 53 is essentially the other answer, the so-called the food specific attack rate. Okay. These two, I realize that these two is, in the language wise, is a bit subjective. So the proportion of patients who ate the wedding cake, 50 over 54, that's the best answer. That's why the last one is a food specific attack rate. Okay. So there's a lot of argument with this question, I can tell you. All right. Question 5. Your question 5 is what?
Smoking and blood pressure.
Okay, smoking and blood pressure. Okay, smoking and blood pressure. What is the odds ratio? Whoever answered just now.
So can be either.
No, this one is odds ratio because it's a case control study.
No, I'm talking about the fraction. I'm sorry.
Okay, this fraction, right? Because 50 over 54, the best answer is a proportion of patients who ate the wedding cake. So the only remaining answer is for the last one.
But you just now say the arrow, you say the very subjective.
Correct, because technically 50 over 53 can also be considered as the proportion of patients who ate the wedding cake. Yeah.
Shit.
But now it's just by elimination, which is the best answer to give. Yes, what?
Sure. 50 over 54 is not the proportion of patients who ate the wedding cake, right? Because 4 people didn't eat the wedding cake. So they didn't
yeah lah. So because but they're still ill, that's why. Correct. So there's still 4 ill. So how many of those people that fall ill actually ate the wedding cake? That's what I'm trying to say.
Because very ambiguous, like they say food specific attack rate. If they change to cake specific attack rate, then it's like more.
Yeah lah. That's why this part is subjective.
Okay, can.
Yeah. Okay. Okay, so question number 5. The odds ratio is about 2.16. Okay. And question number 6. What is the question number 6?
Wait, Joe, can you repeat why cannot RR?
Because it is a case control study.
Okay.
Okay.
Why case control?
Okay. Okay. The study is to find out whether smoking increases blood pressure. Okay. So you have a group, the exposure is known. Then you actually trace backward to see whether the outcome is known. So you trace backward to see the exposure. Okay. Now, frankly, case control study and cohort study is always messed up. Unless you are very used to it, it's easy to get confused.
Wait, so the high blood pressure is the outcome.
Yes, high blood pressure is the outcome.
Okay.
Okay. Now, in reality or in practice, since you can have all the numbers, right? Most of the papers that we go through, most people will just calculate relative risk and odds ratio, whether is it suitable or not. Okay.
Will minus mark me like that?
Actually, we never really asked such question before. We never really asked whether can you use one or not the other. We will to let you score a bit better. We will just ask you what is the relative risk or what is the odds ratio, and then you can calculate the correct thing for us.
Nice. So a case control study is always odds ratio.
Yes.
So what about cohort study?
Or you can use relative risk or odds ratio, up to you. And in relative, we always do both.
Wait, Dr. Ling, since this is Alexander, since we are on this topic, right, I'm still really confused because like if later we go down to question 8, right, they do the observational or experiment, right?
Yep.
Isn't like experiment just case control, but then end up is cohort study?
Yes, that's a problem. That's why it's very subjective to some extent. In concept, you can tell it very easily, but in practice, it's actually not that easy.
Oh.
Yeah, reality that's a tough part of science. For example, right? Do you know what is the worst thing that geologists like to be asked when they go to talk in secondary school or primary school? You know what geologists, right? You know what they are most afraid of being asked or what they hate being asked when they go for a talk in, let's say, any schools, for example?
What the position of the tectonic plates?
No, students will just bring in a random stone and ask them to identify. Seriously, that's the toughest because when they are start going through their degree and they're going through a training, they look at pure samples. Even a piece of brick, when it's weathered enough, nobody can tell whether it's a brick or a stone or a natural stone, unless you do chemical tests and all these things. Yeah, so it's kind of a similar situation here. Okay. All right, so let's continue before anything else. So question number 6 is which one? What's your question number 6?
Vaccine.
Vaccine?
Vaccinator.
Oh, question number 6. Okay, the chickenpox one, right? Okay, the chickenpox. Yeah. Okay, so what is your risk ratio? Risk ratio is actually relative risk.
Cannot OR.
Both can be
everything
used.
also can.
Both can be used.
Okay.
Yes. So what is your relative risk? Hello, people. Someone respond. Clara, what is the relative risk?
Wait, teacher, I don't know how to do this question.
You don't know how to do it. Okay, so let's see. Okay, so let me just change this and I'll just write it out for you. Okay, save. Okay. Laptop, are you going to save for me? Okay. Okay, so question number 6. So let's see. Question number 6. What you have is the You have chickenpox. No. Chickenpox. Okay. Vaccinated. Unvaccinated. Okay. So now you have 18, 3, 1, 3, 4, and 4. Okay. Now, so you have to look at what is the risk. The risk of developing chickenpox. Okay, the risk of developing chickenpox is essentially here is 18 over 134. No, 18 over 134 plus 18, which is 0.118. Okay. So here is 3 over 3 plus 4, which is 7. This gives you 0.429. Okay. Then your relative risk is really the risk of developing chickenpox with exposure. The exposure is the vaccination over the risk of developing chickenpox without exposure, so without vaccination. Okay, so essentially this is 118 point divided by 0.429, which gives you 0.275. Okay. Now then the conclusion will means that those children vaccinated have about 1/4 the chance of developing chickenpox. Anyway, anybody know what's the actual name for chickenpox? What's the scientific name for chickenpox?
Is it varicella?
Yeah, correct. Okay. All right. Okay. What?
Can say that they have 80% less chance of developing.
80% less. About there lah. About 80% less chance. It's about 78% less chance. 79% less chance. Correct. 28% less chance.
Wait. Then can you calculate the OR for me?
What do you calculate OR for you?
Cause like I don't know I can't use OR ma. I don't know I thought correct or not.
Okay, calculate yourself. Give me answer.
Allow.
I don't have a calculator with me. Quick.
Okay. Relax. 0.179.
0.179. Yeah, correct.
Okay, thank you.
Now you always yeah. Who stopped just now?
So we can use either odds ratio or relative risk, right?
This case, yes.
Okay.
So you actually realize a kind of a heuristics. I was going to say a rule that when relative risk is more than 1, okay, odds ratio is larger than relative risk. Okay, when relative risk is less than 1, odds ratio is less than relative risk. Okay, like for example here. Okay, so this is more or less a heuristic that I kind of use to check whether it's a calculation right or wrong. Okay, what is your question 7? Yes, who?
So both answers from RR or OR are like accepted. You can
Yes,
just put
yes,
one.
yes. Yeah.
So it means that like when they ask you which one you can use, like you just cannot use relative risk when it's case control, is it?
Correct.
But in any other situation, like both also can.
All right.
Okay,
But
thank you.
usually for test question, especially now is online test, right? To make our marking simpler, we don't ask you which one you can use. We ask you to calculate the relative risk or calculate odds ratio or calculate, yeah, basically answer the question.
So if they just say find the measurement of association, you can do both lah.
You can do both, but again, I tell you that because we seldom want to set such exam questions or test questions, we will prefer to set question that this is the result, or this is the numbers. Calculate relative risk to 3 decimal places, and make sure you have 3 decimal places. Because if you put relative risk to 3 decimal places, the computer will mark for us rather than we could have to go and mark ourselves. Understand or not?
Hi, teacher, can you repeat? Sorry.
Okay, so normally in test, what we will do is we will ask, for example, we give you this table. And then we tell you to calculate relative risk to 3 decimal point or 3 significant figures. Then you calculate that result. Understand?
Yes, okay.
Yeah. Because if you do that and you put, let's say, 3 decimal places, right? Maybe you put 1.242. And if my answer in LMS is recorded as 1.242, LMS will automatically mark for me. So I don't have to mark.
Then what about odds ratio?
Same thing lah.
Okay.
Yeah. So think about why would I set a question that say use any method, and half the student use odds ratio, half the students use relative risk, and then I could go and check all the 100 students. Right?
So you always say when to use odds ratio.
Normally we will do that unless you think I got so much time to go and look at all your answers if the computer can mark for me.
So even when it's case control, you also say to use relative risk.
We normally say that. It's very little chance you don't say that. Okay, next question.
Oh wait, one more question. So like I can say it's 18% less chance that you'll get chickenpox.
If you use odds ratio, yes, 80% less chance, correct. In fact, it's a bit more than 82% less chance. Yeah.
82.
Okay.
Oh.
Yep. Okay, so what is your, just now is question what? Question 7. Or question 6. So what's question 7 for you?
Forming whatever.
Forming. Okay. Performing. Where's my performing question? Performing question. Where the hell are you? Okay. So question 7. Okay. Now question 7. Here you have relative risk and odds ratio. What is relative risk? What is odds ratio? Calculate both.
They ask you calculate both, man.
Either one can be used because it's cohort study. So for those who have calculated, what's the answer? So for you, what's
relative?
your
Sorry.
Yeah, continue.
Oh no, I was saying relative risk I got 2/3, but then I just convert to decimal place, so it's 0.67.
Correct. Yep. Odds ratio?
0.615.
Correct. Yep. Okay, question 8. Last one. Question 8. Okay. Last one. Which table is correct?
Table 1.
Table 1, correct. So use table 1, because table 2, the rows and columns are opposite. Where am I? How come? Okay. So table 1, yeah. What kind of study is this?
Experiment.
Yes, experimental study. Okay, and since experimental study, what is the, ask you to calculate, what is the risk? What is the relative risk first?
0.7.
Yep. Okay, 0.69 something, so 0.7. So it means that prevastatin reduces non-fatal myocardiac infarction risk. Okay. All right. D. How about D?
Teacher, you don't say by 30%.
By about 30%, yes.
But like, is it not always need to put in the number?
You can lah. You can reduce by about 30%.
Sure.
What?
So this is an experimental study. So it is case controlled, right?
Experimental study need not be case control as well. Yeah. So again, it's subjective lah. You can tell, but the question here asks you what is the risk? What's the reduction?
Oh, okay. I retarded. Okay.
Yeah. Okay. So part D.
Wait, so cannot use odds ratio to calculate?
No,
like
because
what?
the question asks you what is the reduction of risk, ma? It's not the reduction of odds, ma.
Oh, okay.
You know? Yeah. Okay. So
sorry. So this one is if they never ask, right, then they ask you to calculate the measurement of association. Then can you use both?
Can. In fact, question E that you can use odds ratio as well. So this is for A, this is for B, this is for C, for E, right? Yes, you can use. Yes, you can use odds ratio as well. Okay, how about D? Can. This is something that I have not learned yet. The 95% confidence interval of the relative risk is between 0.5799 and 0.8443. So do you conclude that it's effective or not?
No.
Yes, it's effective.
Shit.
Yes.
Teacher, for question E, do we need to explain?
In this case, you want to explain also can, because it's technically a cohort study.
Also, you can just say the reason is because it's a cohort study.
Okay. So because it's effective because basically the 95% confidence interval does not include 1. Okay, this you wait until when we talk about confidence interval, then we'll talk about it. Okay, but essentially that's a reason. All right, any other questions?
What you mean? What less than 1?
Okay, does not include 1. When we go to the chapter on confidence interval, then you understand what this means. So this is a bit beyond the confidence interval, but beyond the syllabus for now.
But what you mean by it does not include 1? Because the solution say this is because the entire range is less than 1.
So basically your interval is from here, 0.5799 to 0.8443. 1 is here. So your interval is less than 1.
Oh, okay.
Okay. All right. If there are no further questions, that's all for today. So
I have a question.
Yes, what question?
This is about the further clarification slides, like for.
Huh? Further clarification on what?
is on topic 2, the one that I asked Dr. Yang.
Oh, I have no idea what you asked her. I don't.
Okay. It's on actually topic 2, example 6, the sample spaces S and on.
Okay, hold on. Topic
Yeah.
2. Let's see if we can pull out topic 2 first.
I think it's like 20, if I'm not wrong.
Hold on. Alright, where's my mouse? Okay, this thing killed. Mouse. Okay, that's my head. Okay, now problem topic 2. Topic 2 or topic 3? Topic 2. Lecture, PowerPoint. Topic 2, 3. 2 or 3?
It's 3.
Okay, 3.
But like on LMS, it's called like the topic 3 further clarification slides.
Which I have no idea what. Okay, let me see. If we want. Okay, is it which one? Slide number.
I don't think it's included in the normal slides.
Okay. Oh. Let's go to your LMS. LMS, where are you? Okay. Like in lectures, right?
Yeah.
Okay.
Topic 3.
Topic 3. Further clarifications. Okay. Which slide?
Slide 3. The last question in slide 3.
Okay, last question in slide 3. This one. Alright?
Yeah, the throw a dice twice.
Okay. It's equals to throw a dice twice. What's the probability of getting a sum? Are the two events independent? That means, are the two events related to each other?
Yeah, I'm not sure how to do like that question.
Okay. If when you multiply up, that is the probability. So you almost say it. So it's the same thing. If example is you throw a dice twice, what's the probability of getting the sum value 1 plus value 2 equals 2? So one of them, in order to get value 1 plus value 2 equals 2, right? You have, that means 2 dice, both of them must be 1, 1 each, correct?
Yeah.
Okay. So if you can multiply up and the combined probability is equals to the multiplication of probability, then the events are independent. That means one event does not affect the other event.
Yeah, but then like if it's equal to 4, then there would be like few numbers, right?
But it's the first the question is asking you, is the first dice, the result of the first dice affecting the result of second dice?
Okay.
You know, it's not, huh?
Oh, so then you say it's not independent.
Huh?
So how do you answer the question?
Okay, if there's one dice, that means the first dice throw, you take one dice throw, right? Does the first outcome affects the second outcome?
No, it doesn't.
Yeah, I don't know. You know? So basically the first dice throw doesn't affect the second dice throw.
Yeah.
You know? Then how you want to answer it? It could be, what are the ways of getting a 4? So it can be, to get a 4, you can be 1, 3, 3, 1, 2, 2. So there are multiple options. But here we never ask you to calculate, because calculation is a lot more messy.
Yeah, but I want to see the calculation.
Okay. So if you look at it, right? Oh. Okay. So how do you get 2 dice throw equals to 4. So the outcome will be 1, 3, 3, 1, and 2, 2. Okay, so which means that the probability of getting a 1 and 3 is times the probability of getting a 3, the probability of getting a 3 and 1 is probability of getting a 3 times the probability of getting a 1. Okay, probability of getting a 2 and 2 is the probability of getting a 2 times the probability of getting a 2. So each one is 1, 6 times 1, 6. Okay, each one is 1 over 36, 1 over 36, 1 over 36. Okay, the probability of getting a 4 in 2 throws is equals to 1 and 3 plus 3 and 1 plus 2 and 2, which is equals to 136 plus 136 plus 136, which is then equals to 1, 2, 3, 3 over 36, which is the same when you go to look at our table. 3 over 36 is the same as what we have for, and where is my, our dice throw problem. Dice throw, where are you? Yeah, this 3.
Teacher, can I just ask, why do you have to like go through the long method? Like, why you cannot just like look at this like table and just see that it's 3 out of 36?
Yeah, because that's what you asked me to do, ma.
Oh, so but then
you get this, you expect 3 out of 36. When you do the calculation, it is 3 out of 36. Therefore, it is, you get this, right? And then it will come back to this. The way you the two numbers, when it's tally, it means that the events are independent.
So that means you must do like both methods to find out if it's independent.
Right.
Oh, okay. So it's very long-winded.
Hello. That's why I told you, because 2 is easy. You go back to here, 2, there's only 1. So 1 of 36, oh?
So actually, right, to find out if it's independent or not, for like the first example, the one where it's equal to 2, you actually have to do this thing. Oh, okay. Thank you.
Okay.
but teacher, isn't it like common sense that 2 different dice does not affect each other?
It's common sense, but mathematically there's no such thing as common sense. Mathematically, it's logic.
Oh my god, so I have to write down now.
Yes, of course.
Oh my, okay.
Yes. Because mathematics, there's actually a lot of dilemma and paradoxes.
So mutually exclusive means that the results of one don't affect the other, right?
Mutually exclusive, no. Mutually exclusive means that the multiplication of the probability equals to 0. This is independent. Mutually independent and mutually exclusive are two totally different things. Mutually exclusive means that well, it cannot be a day and night at the same time. The two events cannot happen at the same time. Let's call mutually exclusive events.
Then independent is both can happen at the same time.
Yes.
Yes.
Okay. Independent simply means that both can may happen. May happen doesn't mean that it should happen, but one event does not affect the other event.
Okay, so to find out if something is independent, you do the A intersect B equals to PA times PB. Huh?
You do this whole calculation, no? Yeah.
This whole calculation. So if there's the commonality, that means the 1 over 36 lah.
Yes. Actually, it comes out to 36, which is what you have in your this as well. This also 3 over 36. There's only 3 outcomes. Because the two number tallies, it is an independent event. If the two numbers do not tally, then it's a non-independent event.
Teacher.
What?
What is sampling without replacement?
Sampling without replacement means that, let's say you have a bag of for example, you draw lots. Okay, sampling with replacement means that you take you draw a piece of paper or you draw something, you don't put it back. That's called sampling without replacement. That's called sampling without replacement. Sampling with replacement means you take out, you read, and then you put it back into the box again.
Okay.
Okay.
Teacher, you're not gonna go through question 1.
Okay, question 1. Question 1. Okay.
Sorry. I want to ask. Sorry, the last question D, right? Can you use difference of proportion?
Last question D.
Yeah.
Why difference of proportion? What is called proportion?
I don't know, because we all never learned this question before, and then you all come out with this question. And
that's why tutorial do. That's what tutorial have to do.
So what's the use of difference of proportion? It's to find relationship, what?
Yeah.
Then this one cannot meh? Effectiveness.
Oh, you're talking about which question first?
The confidence interval, that one.
That's why. Okay, this don't bother our confidence interval until we come to that, because you have no idea what confidence interval yet.
Then what is the use of difference of proportion?
Difference of proportion is you are looking at one over the other. For example, let's say in this, what is the risk of, rather, let me just go back. What is the risk of, or what is the reduction of risk from not vaccinated over vaccinated? That's the difference in proportion.
What is considered substantial?
There is no gauge at the moment. If you want to consider what's substantial, then you have to do a hypothesis testing. It's a totally different story.
Okay.
That means is 0.8 enough? Is 0.7 enough? Is 0.9 enough?
Okay.
All right. So question 1. Okay, question 1. Question 1 talks about the difference in proportion. Is it correct or not? True or false?
Which one?
Question 1A.
True.
Correct. Because difference, you learn in your maths before, difference means subtraction. Sum means addition. Okay, 1B. We always have an option to use either relative risk or odds ratio to measure association between two categorical variables. True or false?
False.
False, correct. Because your case control, you should not use your odds ratio. Working as a barrister and being a TP student are mutually exclusive events. True or false?
False.
False, because you can work part-time. Okay. If I sample without replacement, the future probabilities are unaffected.
False.
False, correct. Okay. For intervention that increases the chance of events, odds ratio will be larger than risk ratio.
True.
True, right? So it's basically this thing.
Sorry, the first, what's A and B again?
A and B, A is true, B is false.
Thank you.
Okay. All right, then that's all for today. Have fun. I'll post the. I'll post this anyway. Well, I'll post this when I'm done, and I will put the video on YouTube when I'm done as well. Okay.
Increased chances of event.
Yeah, teacher, can you explain question E?
Sorry.
This one. When relative risk is more than 1, odds ratio is always higher than relative risk. So for intervention that increases the risk of a chance of an event, odds ratio will always be larger than relative risk. It's mathematical.
Okay.
Yeah. Okay. Any other questions?
Actually, yes, I got the topic 2, the example 6, that one I really don't understand.
Okay, then don't bother understanding if you don't.
Oh, okay.
Yeah. Go and think through. If you really cannot understand, then try to scratch your head a bit more times.
No, it's the independent event, like the calculation, because Dr. Yang said she'll post, but then never post.
Slowly wait lah. Maybe she will post later. Okay. Let me. All right, then that's all for today. Have fun. Bye-bye. Okay, bye-bye. Nobody want to leave,
Miss you, Ma.
Forget it. Bye.
Thank you, bye-bye.